Now we're going to talk about steady state error, the general case of steady state error, kind of depicted on this chart for a step input. It's what happens out in steady state, but we're not always going to look at a step input. I'll talk about the other types of inputs we could consider. And we're looking for, what is that, as time goes to infinity, that error. And to remind you, the system we're talking about is depicted in this block diagram here. We'll have a controller, a plant or a process in the forward path, some H in the feedback path. And we have two different inputs here. We'll ignore this noisy sensor input, but we have the R that we control, and as a disturbance input we can't control. The response of this system to the two different inputs will be the sum of its response to each of the inputs individually. So we're going to need to look at two different transfer functions, one from R to Y and one from TC to Y. And typically, I'll just say the error we're going to concentrate on is R minus Y. This input at the very beginning and the output. We're going to compare the input and output. It could be the error you're concerned about is something else. Maybe the R and Y don't even compare. They might not even be the same units. The method we're doing here is you got to find the total response, and the error is however you define it. And then we're going to apply the final value theorem. So if you forgot the final value theorem, it's way back in the first module of this course when I'm talking Laplace transforms. But anyway, let's say the error we're going to concentrate on is R minus Y. In the Laplace domain, it's big R minus Y. I could rewrite this error this way. And this is our normal transfer function from R to Y. We'll call that T, the transfer function. So here's that error when we're talking about the input R. We call that the tracking error. How well does the output compare to R? Here's the transfer function for that. Then there's the error due to a disturbance. Remember the superposition principle, which we talked about much earlier. When you look at one input, you set the other inputs to 0. Up here, we set the disturbance input. Now we're looking at the disturbance, we set R to 0. So the error being R minus Y just becomes minus Y. So that error is just minus Y, and from Y to TD had a little bit different transfer function than this transfer function. It's got this extra decent C in the numerator. All based on that block diagram I just showed. By the way, here's just a useful tip when doing some of the algebra. Remember, here was the good old formula for feedback, where the whole forward path gain we just said was G. Not quite the G in the block diagram we just had. Well, the G and the H would both have a numerator and a denominator. Put them into here, and here's how to calculate this transfer function given those numerators and denominators. You can kind of think of well, let's look at an example. Let's say here's our G and here's our H. What's the transfer function? Well, down in the bottom, it's the product of the two denominators plus the product of the two numerators. So the S times S plus 4 times S plus 6 on the bottom plus 100 times 1. That's the denominator. And on the top, it's this numerator times that denominator, 100s. Write that down somewhere, put it on a formula sheet, or just memorize it. It saves you some time. Okay. I said we're going to have inputs other than just a step input when we talk about steady state error. And we're only going to consider 3 of them. A step, a ramp, and a parabola. A times t, 1/2 at. In the Laplace domain, they are these, just a over s squared, and a over s cubed. Got it? Those are the only inputs we're going to talk about. So let's do an example. We're going to say this k here is equal to 0.4. Find the unit step tracking error. That's part A. And then find a g sub p to make the unit step tracking error be 0. First, you need to find the overall transfer function. Well, this thing is just going to multiply it. But here we have a sort of g over, we have a g here and an h here. So we use the trick we just talked about. See, the denominator will be s times s plus 2 times s plus 0.1 plus k, which is 0.4 times s plus 1, or s plus 3 rather. 2 numerators, 0.4 times s plus 3. And then this will be the 0.4 times this guy's denominator. You can go back to the previous chart and do that yourself. And then that all gets multiplied by this g sub p. That's the transfer function. Here is r minus y. There's the error. And we're using the final value theorem. In this case, to a step. What's the final value theorem say? Multiply the thing you're looking at times s, and then take the limit as s goes to 0. Well, the thing we're looking at is this, but r is just 1 over s, unit step. This just tells us what the error is, the transfer function for the error, basically. Well, in this case, these s's cancel, and it's just 1 minus t sub 0. What is t sub 0? Getting zeros for all these s's, and you get a simplified thing. This is going to be g sub p over 30. That's the steady state error to a unit step. Or actually, 1 minus that is the steady state error. This is t sub 0. So the error is 1 minus that. So this is the steady state error. Excuse me, 0.976, 29 over 30. And we could make it 0, that was part B of the problem, by making g sub p equal 30. We get 1 minus 1. But anyway, the overall process is to find an expression for the error in the Laplace domain, and then apply the final value theorem for the type of input you were asked about. Here's a case, I might be running long, but I think it's the only other, yeah. In this case, we'll look at the error from due to a disturbance, a unit ramp in the disturbance. Remember, when we're looking at the error due to the disturbance, we set r to 0. So the error is just minus y. It's r minus y, but r is 0, so it's just minus y. And here we have to use our little trick to get the overall transfer function times whatever t sub d is. If it's a unit step, t sub d is 1 over s squared. And the final value theorem says multiply all that mess, this whole transfer function times the t sub d, which is 1 over s squared, multiply all that by s and take the limit of that whole thing as s goes to 0. So you'll have an s here and s there. They both cancel this s squared. That's good. And the rest of it, you just plug in zeros through the rest, and the arithmetic says it's this, minus 1 over alpha. That's the general method. Sometimes it takes a lot of work. You have to find all the right transfer functions, the right inputs, apply the right inputs to it, step, ramp, or parabola, and then apply the final value theorem. You might need to review some stuff and put all that together before you can do it yourself.